We also have 2 lessons today, right? 3, 4, 5. No, 7, 6. You gotta add the
we're going to get inverse functions. The first 3/4 of this lesson will be theoretically pre-calc review, but realistically, some of you, many of you, all of you have forgotten some of this stuff. So I will be here to refresh your memory, and then we'll dive into some calculus at the end, and I will give you 2 approaches to solve a problem. I have a preference on one of the methods, but obviously I'm going to show you both, because then you can use whichever one makes you happier, because that's my goal, to make everybody happy. I lied, I don't really care. Okay, so we're going to talk about pre-calc stuff first of all. How to determine if 2 functions are inverses of each other. Then at some point we're going to figure out what the inverse is. Ooh, I went quickly on that one. If you're given a function, what is its inverse? And not only is it an inverse, but an inverse function. And we're going to have to make a distinction between the difference of those 2 things. In other words, every function has an inverse, but not every inverse is a function. So we want to deal with inverses that are also functions. And then the last thing, so that the first 2 are pre-calc review, the last one is calculus. And that's the method that I'll show you 2 different ways. And then for today, we're going to try something new. Whoops. Just simply be nice to people today. Okay. Ready? All right, here we go. A lot of gobbledygook in there. Number 1, domain and range. So what's domain again? X values of a function. Range is the Y values. So in this class, what are the 2 things we're concerned about with domain? What are bad?
Holes. Potholes.
Potholes are bad. Yeah, especially if you got low tires. Or potheads. Sometimes those are bad.
But they're pretty funny sometimes.
Sometimes, right.
Yeah, man.
Incontinuities.
That was the.
What causes incontinuities?
Asymptotes.
Asymptote. So what causes an asymptote?
Undefined directions.
Oh, yeah.
Yeah. Undefinitions.
How so?
0 denominator.
Beautiful. First thing we're concerned about. No 0 denominators. What's the other thing? What'd you say?
Taking the square root of a negative number.
Perfect. No negative square roots. Anything else is fair game. For real. Get it? Because we're dealing with real number system. That's funny. For real. No 0 denominators, no negative square roots. Anything else is good to go. So when we're listing the domain of a function, those are the only things we care about. What's going to make the denominator equal to 0? Avoid it. What's going to make the square roots negative, or the radicand negative? Avoid it. Once you get that established, then we start talking about the range. And the range, in my opinion, is usually more difficult to find, so you got to think about all the possible y values. However, one of the things we're going to make use of is that relationship at number 1. The domain of a function is the same thing as the range of the inverse. And the range of the function is the domain of the inverse. Domains are much easier to find. So if I want to know the range of a function, because it's valuable, I'm going to find the domain of the inverse instead, because those should be the same thing. In number 2, we're concerned about 2 things. Number 1, the notation. F to the negative 1 is not a reciprocal. You're not raising that to the negative 1 power. It's just a notation for expressing an inverse. And then this little relationship here. If a function and its inverse are used to create a composite function, those composite functions have to equal x in order for them to be inverses. And yes, you have to check both. You got to put f inverse into f, and you got to put f into f inverse, verify that they both equal x, and we are good to go. Okay. So, are those two functions inverses? Go ahead, check it. Do a little bit of composite function, simplify. It's good for you, builds character. Yes.
Yeah, it is.
What do you get?
X.
For both?
Yeah.
Yeah, everybody good on that?
Yeah.
Anybody having trouble setting up that composite function? F of g of x, go to f of x, where you ever see an x, put in that mess. 2 times the cubic root of x plus 1 over 2 minus 1. Oh, cubed. What happens when you cube a cubic root? Twos cancel. X plus 1 minus 1 equals x. Woohoo! That one works, but as I mentioned, you got to check them both. The cubic root of 2x cubed minus 1 plus 1 over 2. Minus 1 plus 1 cancels, 2's cancel, the cubic root of x cubed, x. Done. Good. Those are inverses. Life is good. And I know you've done that before. So we're going to move on. Questions? Standing. Yeah. Oh, this is the picture we're going to talk about. If I take a function and I graph the function and its inverse, which is what that's a picture of, they are reflections of each other over the line y equals x. Okay. Now, you may have learned in pre-calc that flip it over the x, flip it over the y, or flip it over the y, then flip it over the x. You get the same results. Flip it over the line y equals x. And we're going to use that at the end of the lesson when we start doing some calculus. So this is a fairly important concept to understand. The other thing that we need to talk about is, what if I have a point here, A comma B, right there. If I take that point and I flip it over the line y equals x, it'll end up over here on the inverse. What's the coordinate of that red point? BA, very good. Okay, the x and the y points, the x value and the y value switch spots when you reflect it over that line. So AB is on the function, BA is on the inverse. 1, 2 is on the function, 2, 1 is on the inverse. And we'll use that later. Okay? None of that is new yet, right?
No.
Good. I was hoping that was the case. I said that already. Okay. As I mentioned earlier, all functions have inverses, but not all of those inverses are functions. And we want to deal with inverses that are functions. To do that, we're going to learn 2 methods. One you already know, or should already know. The other one is going to be new because it involves calculus. So one method, if you have a picture of a function, you can use the horizontal line test. Not to be confused with the vertical line test, which tests what? Whether or not something is a function, whether or not an equation is a function. The horizontal line test works the same way. If you draw any horizontal line through the function and hits it in more than one spot, then the inverse is not a function. Okay, so that picture of that upside down parabola looking thing, its inverse would not be a function. That's a function because it passes the vertical line test, but its inverse would not be a function. And we will see all combinations. Non-functions whose inverses are functions. Functions whose inverses are not functions. Functions whose inverses are functions, and then non-functions whose inverses are not functions. I think I got all 4 covered, right?
Yeah.
Yeah. Yes, 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 no, no, yes, no, no. Beautiful. That's one method. Now, that's based purely on the idea that you have a graph of the function or you know what the graph looks like. If you don't, we've got to do something else. And that's where we get into some calculus here. I think the calculus method is easier because you're not relying on a picture, nor are you relying on knowing what the picture looks like. So, blah, 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 blah. Uh-oh. What is strictly monotonic? Any idea?
Mono equals 1.
Mono equals 1.
Tonic. I failed my STEM test, so I don't know.
Tonic, gin and tonic, 21. So 121 here, mono.
Good. 1 and 21. And strictly? Strict from the Latin to enforce.
Yeah.
Lee is Bruce Lee's last name.
He
Right.
died early.
So that means to enforce using violence.
Yeah.
Right.
Well, Lee also has 3 letters in its name. So
He does. Right.
So 3
So subtract 1 E.
21. So
E is equal to 2.1.
I think it goes to 24.
Did you say 2.1?
Well, you guys are really good. Strictly monotonic means always increasing or always decreasing.
Oh, we were close.
You were very close, right? Just off a little bit.
Yin and yang.
Oh, that's what it is.
Knowing what strictly monotonic means, how would we go about checking to see if a function is always increasing or always decreasing? Okay.
Take the derivative and do the line test.
Yeah. Keep going.
Oh, and check, make sure that there aren't any, relative maximums.
Could have said it better myself. Any questions for Megan? Does everybody understand? Yeah, good. If it doesn't have a maximum in, it doesn't change. It doesn't change from increasing to decreasing or decreasing to increasing. And if we're clever about it, we can do it without even doing all that work. We can skip the number line, we can skip plugging and chugging if we use our brains a little bit. So let's take these two functions. We'll do A first. Is A strictly monotonic? Okay, so let me talk you through this. I want to know if the inverse of part A is a function. In order for it to be a function, it has to be the function has to be strictly monotonic. How do we check to see if it's strictly monotonic? As Megan said, you take the derivative and see if it's always increasing or always decreasing. F prime of x is equal to 3x squared plus 1. Now, I could find the critical numbers, put them on a number line, test regions. But let's be sneaky about it. What can you tell me about f prime of x? Christian? Yeah, but that's the derivative, not the function. The function itself is cubic, yes.
That was a quick guess, the variable.
Okay, but again, that applies to the derivative. What can you tell me about values I could get out of the derivative? Evan,
You never get a negative number from it
why?
because it's above the hold on. Because the lowest point is 0, 1.
Trust.
Well, the derivative never goes negative. So
Why?
then
How do you know that? Other than you're really smart.
plug in the 0.
Or, you got three possibilities, right? Plug in a negative, plug in zero, plug in positive.
Yeah.
What is a positive fairly obvious there?
Yes.
Yeah, a positive squared is a positive, plus a positive is a positive. What about zero?
No,
Positive.
positive.
0 squared is 0 times whatever is 0 plus a positive is positive. What if x is negative?
Positive. Positive. Positive.
Negative squared is a positive, positive plus a positive is positive. That's always positive. Therefore, it's always increasing, which means it's always, or it is, I should say, strictly monotonic. Therefore, its inverse is a function. Are you with me so far? Okay, good. Now, that doesn't mean that we can't find the critical numbers, put them on an underlying test regions. I'm giving you some options here. Part B, f prime of x is equal to 3x squared minus 1. And again, Find the critical numbers, put them on a number line test regions if you'd like. But what can you tell me about that function? Is it always positive?
No.
Is it always negative?
No.
So that answer can be positive or negative?
Yeah.
Good. Therefore, not strictly monotonic, and therefore the inverse is not a function.
Just a quick reminder, what does strictly monotonic mean?
Always increasing or always decreasing? Always going up or always going down? Yes, sir.
And are neither of those an inverse?
They both have inverses. The top one is a function, the bottom one is not. The inverse of part A is a function, because it's strictly monotonic. The inverse of part B is not a function.
I was thinking it's a parabola, so then it's not monotonic.
No, this function is monotonic. We care about the function, not the derivative,
And why do we take the derivative?
to test whether it's strictly monotonic or not.
Remember the first derivative test?
Maybe. Okay.
So if you don't need to take the derivative to see if it's monotonic, then why'd you do it?
But you
You do need to take the derivative to see if it's
Why
monotonic.
did you just say you didn't?
Well, why did not?
That's not what I said.
Free real estate now.
Shall we start over? Okay. If that function, we'll talk about A only. If that function is strictly monotonic, then it either has to always be increasing or always be decreasing. You with me there? Okay, so to check if a function is increasing or decreasing, we take the derivative. If the derivative is positive, it's increasing. If the derivative is negative, it's decreasing.
How do we know X is tip? How do we know? Never mind.
You giving up that easily?
Yes.
Since this is always positive, it has to always be increasing. If that doesn't make sense to you, then we could solve for critical numbers here. Okay, so 3x, well, let me change colors here so we're not confused. 3x squared plus 1 is equal to 0, so x squared is equal to negative 1/3, so therefore x is equal to the square root of negative 1/3, which means there are no critical numbers. Okay. Which means my number line would look like this. Plug in a number and check it. Well, any number on that, let's put in 0. I put in 0, it's positive, so this number line is always increasing.
That's it. It's it.
Which means it's strictly monotonic, which means its inverse is a function. Okay? If we did the other one, we would actually get a critical number. It'd be plus or minus the square root of 1/3. Put them on number line test regions, you're going to have a max and a min. For those of you that are graphically minded, here's a picture of part A. You can see that it's always increasing, like we figured. And then here's part blah, blah, blah. Here's part B. Okay. Also, you'll notice in part B, it doesn't pass the horizontal line test. So now that I have a picture, I could also show you the horizontal line test and show that it fails that, which again indicates that its inverse is not a function. Okay. Either one of those will do the same thing. Horizontal line test or using the calculus part of it. And usually the calculus part will work out nicely because you're going to get nice easy functions like that cubic or parabola or something that's fairly easy to take the derivative of. Blah, 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 blah. Okay, so here's some tricks to find the actual inverse. In most of the problems I've given you already, I told you what the inverse is. Or we check to see if f and g were inverses of each other. This will help you actually find the inverse. So here's a function f of x. What's its inverse? And you did this in pre-calc also. There are a couple changes though. Number one is new. I don't know in pre-calc if you started inverses by checking to see if the inverse is a function. You probably just switched x and y and went to town.
Yeah.
Yeah, okay. So in here, you need to start by verifying that that inverse is in fact a function because we want to work with functions. Then you change x and y, you solve for y. Whatever you get for that new value of y is your inverse. That becomes f inverse of x. And I've got an example for you on the next slide that we can take a look at, work through together. That's a good one. That's a good one. It's like the old cartoons where Wile E. Coyote or the Bugs Bunny would have the portable hole that he would slap into something and then make somebody fall through it. That's good. I walked over and there's writing all over the desk. So I was looking at it and then he just picked up the piece of tape and it was the tape that had all the writing on it. So he tricked me. Got him. It's funny. Got him. There goes your grade. Okay. In hindsight, I shouldn't have phrased the question this way. I should have said something like, find the inverse of f of x. Is the inverse a function? But here I'm kind of leading you to the answer already. So first thing we need to do is check to see if that thing is strictly monotonic. So let's take the other route. Get out your calculators or your iPad if you have decimals on there. Graph that function. You might know what that function looks like already, but if you don't, just graph it.
No, I have it current on mine.
Got peanut butter in my chocolate. Chocolate on my peanut butter. Does the picture pass the horizontal line test? Yeah.
It seems like it.
Certainly does. Therefore, that function is strictly monotonic. Now what we want to do is figure out what that function is. What's the inverse of this function? We verified that its inverse is a function, so now I got to grind out the actual work. X is equal to the square root of 2y minus 3. I shouldn't have to ask this question, but I will. What do I do first? Good, square both sides. Then what?
Isolate y.
How?
Add 3.
Add 3. And then divide by 2. Which is the same thing as the inverse of f of x. And we can go back to what we did at the very beginning and verify that by plugging them into each other, but that's silly, because I know that's going to be the inverse, because I just did the calculations to show that it is in fact the inverse. And you kind of get an indication like the original function is a square root. So you undo a square root with a square, so there's that kind of stuff in there. You've got a subtracting 3 in the original function, therefore somewhere you should have a plus 3. You've got a times 2 in the original function, therefore you should have a divided by 2 in the other function. Good? So other than the strictly monotonic stuff, this should all be something we've seen at some point in pre-calculus. And again, whether or not you remember it is still a little shaky. Okay, blah, 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 blah. Yeah, verify it. Okay, great. Now we get to the new stuff. I'm going to show you 2 ways to handle this. Some of you will prefer the method that I don't, only because you're memorizers and you just want a formula to plug and chug into, which is okay. I don't care as long as it works for you. However, this formula can be fairly confusing. My other approach involves a graphical look at the function itself. We'll just go through it. Okay. I want to know the derivative of an inverse function. So let's suppose I have a function f. I want to know what's the derivative of the inverse of f. So you could find the derivative, you could find the inverse of the function and then take the derivative of that function. That's one approach. So I lied. I actually have 3 approaches for you. Or you could use the graphical method that I'm going to show you, or you could use the formula. But before we get into any of those, let me show you a couple things. Suppose I have a function here, something like this. We'll call that f of x. and I've got a point on this function, a comma b. What does the inverse of that function look like? How do I get it?
Flip it over x, y.
Flip it over y equals x. Yeah, close enough. Okay, now the hard part.
Can't you just copy it? Flip it? Twist it? Bop it? Chop it? Bop it? Sorry.
Where's this point?
BA.
BA. Okay. So what does it mean to take an inverse? Sorry, not inverse, wrong question. What does it mean to take a derivative? What are the three things a derivative represents? Rate of change.
Slope of a line.
Slope of which line? Tangent line. Which velocity? Is that you talking? Which velocity?
Instantaneous.
Instantaneous velocity. We're going to use the second one. Slope of the tangent line. So the problem would say something like, what is the derivative of the inverse at the point, let's say, B? In other words, what, ooh, that's horrible. All right, we're going to wing, I'm just going to make it fatter so it looks better. What's the slope of that tangent line at B? That's what the question is asking. I'm going to take a different approach to that. Instead of finding the slope of the blue line, I'm actually going to start by finding the slope of the orange line, which would be something like that. That I can do. Take the derivative, set it equal, not even set it equal, take the derivative, plug in A, I get my answer. And there is a relationship between the orange line and the blue line, which I'll get to in a second. Okay, but this is the graphical approach. In order to find the blue line, I'm going to work purely with the orange line and do one last thing at the end, which I'll get to. Okay? Are we good with this concept? Okay, the end. All right. Now, for those of you that want the formula, there's the formula. Go ahead and write it down. And again, if this makes more sense for you, then by all means use it. Whatever's going to help you, excuse me, whatever's going to help you the most, I'm great with. Okay, good? I'm going to skip ahead to this example then. I've got a function, 1/4 x cubed plus x minus 1, and I want to know the value of the inverse of x when x equals 3. And then I want to know the value of the derivative of the inverse when x equals 3. Okay. Problem is I don't know the y value. Because remember, the x value of the inverse is the y value of the function, and the x value of the function is the y value of the inverse. You with me so far? Good. So how do we do that? This is the key to using my approach, and that is you have to get the 2 points squared away. Because because 3 is the x value of the inverse that we're looking for, we need to find the y value. Okay? And you'll have to trust me on this, where the x equals 2 came from. What I did is I took the function, set it equal to 3, and solved. And that solving is a little wishy-washy there, because solving a cubic is never easy. But we're just going to go with it. Pretend you could figure out easily where that x equals 2 is. So what that is saying is, if f inverse of 3 is 2, then what's f of 2? 3. Okay. This is the relationship that's going to give you problems, but also help you solve the problem. Because now I know where the x value of the original function, all I need to do is take the derivative and plug in 2. And that'll give me the slope of that orange line that we're looking for. So, f prime of x is equal to 3/4 x squared plus 1. So what's f prime of 2? Hmm? 4. Good. Okay, so let me stop for a second and make sure you understand that. In this picture, what is 4?
Slope of the orange tangent line.
Slope of the orange tangent line. Okay, is everybody good with that? Do you see how I got from BA to AB? How I went from 3,2 to 2,3? Okay, good. So now I know the slope of the orange line, so here's the key to the whole problem. What is the relationship between the slope of the orange line and the slope of the blue line? It is the following. The slope of the blue is the reciprocal of the slope of the orange. Not an opposite reciprocal. That's perpendicular. Just a reciprocal. So if the slope of the orange line is 4, what's the slope of the blue line? 1/4. Done. But again, if you're completely confused with this picture or it doesn't make sense, then go back to the formula. But I think this makes a little bit more sense. I'd rather work with the original function than have to worry about what the inverse is and all this other stuff. I will say, or reiterate again, this is going to be tricky, finding out where the points are. But again, if you remember that the x on one is the y on the other, and the y on one is the x on the other, it shouldn't be that bad to put together. That's a line. Keep doing that. So blah, 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 x equals 1/4, which is what we figured. Now, that's how you would use the formula to find the answer, but notice the answer through the formula is the same answer we got by using the graphical approach. And so that gives you 3 possible ways to find that value of the derivative. Okay. Questions? Any part of that that's not clear? I'm sure a lot of it's not clear, but anything that you're completely confused about on that? Okay. Good. Some of it's going to come from practice. Some of it's going to be having you determine which method works best. The other method I didn't really talk about nor give an example of is we could go back to the original function, figure out what the inverse is, especially for a cubic. That's not that bad. It is kind of ugly, but it's doable. Take the derivative of that thing and plug in 3. But usually in a problem like this, they're going to avoid nice inverses and give you ugly inverses so that you don't use that method. You kind of get forced into not using that method. I get nervous when it gets really quiet. Like your brains are fried. Are your brains fried? That's why it's quiet. Okay. You lose the ability to speak. Okay. Another example, same thing, blah, 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 blah. Done. Okay, inverse functions. Not my favorite topic, won't be your favorite topic. Not crucial, but will pop up at some point in the AP test. At least 1 or 2 questions. Okay. For real? Why would I lie? Have I ever lied to you before?
Yes.
I don't know my parents.
When?
Jesus. That was pretty sure.
Hold on, let me stop the recording, Jacob, before you go on a rant.
No.
No.
Good.